Okay, we're going to work problem 8.23 from the end of the chapter. This question asks us to write full electron configurations for 3 different elements. Specifically, we're talking about atoms that are unionized, and we're talking about the ground state electron configurations for each. This is actually a major learning objective for chapter 8, is writing these electron configurations, not only for neutral atoms, but also for ions. We hope that you master that. That's one of the 2 major things. The other tail end of the chapter is on periodic properties, to predict properties of elements. But this electron configuration business is sort of a serious topic for your next exam. So you'll want to invest some time learning all about it, okay? So basically the way it works is through this off-ball principle or building up principle from low energy atomic orbitals up to higher energy atomic orbitals, and there's basically an ordering or a listing. This ordering or listing is presented in your book. Let me again try to find a page number. I think it's maybe 335. Let me see here. Yeah, 335. On page 335 there is a listing of orbital energies. Maybe I should just spend a few minutes and write that over here. What it's got is a y-axis, semi-quantitative energy axis, and down here at the bottom is the 1s orbital. Okay, then up a little ways is the 2s orbital, followed by the 2p, and then up a little ways from there is our 3s, and then 3p, and so on, okay? 3p, and I'm not really paying a tremendous amount of attention as to where I draw these lines. I'm just kind of ordering them, okay, in order of increasing energy. And this is actually kind of crucial for all this, as it turns out, for reasons that we're kind of going to discuss and get into here in a few minutes. But we got the 3p, the 4s is next after that, then the 3d, and 4p after that, followed by 5s, 4d, 5p. So it kind of gets pretty confusing for just to make a list for these higher levels. So after the 5p, we've got the 6s, the 4f, and 5d. Yeah, these are all atomic orbitals, or places where we can put our electrons. So after our 5d, 6p, 7s, 5s, or 5f, sorry. So anyway, goes on and on. There's a whole long list of these, okay? Now, I mean, if you want to, you can kind of memorize the order in which these orbitals fill. But I think a way to do this that's a whole lot easier is just to learn on the periodic table how the different blocks, like the S, the P, and the D block, correspond to electron configurations and how electrons go into the atoms. It's much, much simpler, I think, than trying to memorize this list, which is not going to make a whole lot of sense to you. So I tend to use the periodic table approach, okay? And then remember a few exceptions here. But just to kind of go through this, just to see how it works, okay? Let's just go through these examples. So we got this element, rubidium atomic number 37. The fact that it's a neutral atom tells me that I've got 37 electrons that I need to assign addresses to. All right, I need to put 37 electrons into these available orbitals. So how do I do that? Well, it makes sense that my electrons are going to begin by going into the lowest energy orbitals possible, and then we're going to build up, build up, build up, fill in the addresses as necessary, okay? I've heard it likened to, like if you go to a shopping mall and you have to park your car at the parking lot, usually most of those very, very close parking spots are all filled up. And if you want to get a parking spot really quickly or easily, you got to kind of park far from the mall and then sort of just walk in. That's I guess, a higher energy parking spot, if you will. Okay, so it works the same for our atoms. We fill in the low energy spots first, and then we build up. So I got to fill in 37 locations. So I got a little bit of work to do. So I'm going to start in my lowest energy orbital, which is my 1s atomic orbital. Each of these lines or orbitals can hold a maximum. Well, as I've drawn it, the s orbitals can hold 2 electrons, the p can hold 6, and so on. We'll get into that in a second. Okay. But the 1s can hold 2, and then the next available place is my 2s. That can also hold 2. Now to my 2s comes my 2p. Now p-type orbitals can hold 6 electrons. Okay, so as of right now, I have used 10 of my 37 electrons. So I need to keep going. Now after 2p, I go to 3s. S-type orbitals can only ever hold 2. So I've got 3s2. After that, I've got my what? My 3p6. Now I added 8 more, so I've got 18, I believe. Okay. So I'm through my 3p6. What comes next? My 4s. Now s orbitals again only hold 2. So now I should be at 20 electrons used. Okay. Now after that is my d. So 3d. Turns out my d orbitals can hold 10 electrons. So they got lots of parking spaces or lots of addresses. Okay. And after I do this, I should be up to 30 electrons that have been consumed or used and assigned addresses to. Now my next available spot is my 4p. I'm going to put 6 electrons there because p orbitals can always hold 6. And at this point, I believe I'm at 36, and I only need 1 more electron to assign to get to my number 37. So where should it go? It should go to 5s1. Now s can hold 2. But I'm running out of electrons. I've only got 1 left. So I'm going to write 5s1. And that's my full electron configuration for the ground state of this neutral atom. Now, if you look for atomic number 37, rubidium RB on the periodic table, where do you find it? It's in group 1, right? Now what did we learn about group 1 elements when they form salts and they ionize? Don't they form +1 ions? Give off an electron. Guess which electron they give off? They give off this last one, this valence electron. We call that a valence electron, the highest principal quantum number. They give off this valence electron that's the least tightly bound because it's the electron in the highest energy orbital. When they get rid of that s electron, that goes away, but all the other core electrons remain. And the beautiful thing is if we give this up, the electron configuration becomes identical or isoelectronic to the previous noble gas. Now in this case that's krypton, element number 36. That imparts a special stability to the atom, and that's a sort of a good thing from an energetic perspective. Okay? So we can explain from the electron configuration now why certain elements give up the number of electrons that they do. Because it's ultimately because of atomic orbital stability in the entire configuration. Okay? All right, wonderful. So let us move on then. And I'll actually one more thing before we do. Okay? There's a shorthand notation for this that's actually a little bit easier. Or condensed notation might be another way to say it. Because of this business of the noble gases, like I just talked about, sometimes you might see the electron configuration in a condensed notation written like this for this atom. And what it is it's just in parentheses Kr and then 5s1. Okay? This parentheses Kr is representative of all of the core shell electrons. Basically, it's equal to all of this business right here. Okay? Everything to the left of the 5s1. And the reason why I wrote Kr in parentheses is because it's the previous noble gas. It's element 36. It's got 1 less electron here than the element that we're considering. Okay? When we use a shorthand notation, we're saying that that core, that krypton core, is identical to what it is here in this element. Okay? But the only difference is what's after that core. Here, that's the 5s1. All right, so it's a lot easier just to write this than to write the whole thing out. But nonetheless, we're gaining some experience in practicing. So let's move on to the next element, germanium element number 32. It's got 32 protons, and because I'm dealing with a neutral atom, I have to assign locations for 32 electrons. So I do it exactly the same way. I start the lowest energy orbitals and move towards higher. My 1s can hold 2, my 2s can hold 2, my 2p can hold 6. After that's my 3s. My 3s can always hold 2. After that's my 3p. My 3p can hold 6. After that's my 4s. 4s can hold 2. After that's my 3d. 3d can hold 10. So I think I might be getting closer to 32. Let's see, I've got 4 electrons used. Here's 10. This is what, 20, 30? So it looks like I'm at 30 electrons used right now. I'm too short. I need 2 more. So what comes after my 3D? My 4p. Now p can hold 6, but I've only got 2 left. And consequently, I write 4p2 to finish off my electron configuration. So you see this kind of, I mean, it's a pretty simple idea or concept in general. The only trick to it is that you have to remember the orbital energies or use your periodic table to do this. And, keep good count of electrons. And then I guess you also have to remember how many electrons can go into each orbital. So S can hold 2, P can hold 6, the D can hold 10. Okay? That's what we've seen so far. Okay, so moving on then, let's try argon. It's element 18, which means it's got 18 total electrons. So we start always in our 1s, and then we move to our 2s. Now I've used 4. My next available level is the P2P. I've got to use 6 more. That gets me to 10. Now I am at my 3s level. I'm going to fill in 2 more of those, and then after that, I've got my 3p. I'll give it 3p6. Now, if I'm not mistaken, I think I've used all 18 at this point. Okay. Now, argon is in the last column, last vertical column of the periodic table. It's known as a noble gas, right? Every element in that column is a noble gas. We learned that earlier in the semester, hopefully. And these materials are notorious for being chemically unreactive. The reason that chemists attribute to this fact that they're unreactive is that in all the noble gases, your valence shell, which is the highest integer n, right? Here that's 3. The highest primary quantum number. But that valence shell in a noble gas is full. There is no vacancy for electrons in that valence shell for noble gases. Now, if I was to make this a 3p5, all right, not that the p could hold 6, so there would be a vacancy for an electron there. All right, now what element is 3p5? Well, it would be 1 to the left of argon in the periodic table, chlorine. Chlorine, an atom of chlorine, will be very reactive because it would be constantly searching to react with something else that would donate or give it an electron so that it could make this a 6, because that extra electron would add 1 right there, and you'd complete that valence shell. So chlorine atoms are very, very reactive. That's why they like to form chloride salts. They pick up 1 electron to make Cl minus, form a chloride salt, okay? And the reason why is because we get extra stability in our atom when we complete its valence shell or fill up all the addresses in the valence shell. It's a good thing for the atom, okay? All right, so this is 823, writing some electron configurations. Keep practicing this because, again, this skill will be really important for your exam, I think.